Hey guys, so in this video we're going to quick introduction to the double slit experiment. So double slit experiment, exactly what it says, it's the double slit. So what it is just imagine like two holes and that's your two slits. So imagine if you have like a little film and the film's all solid, but you have two little slits in it that the light can pass through. So the light's on one side of the card or one side on the film, and the light can only get through those two little slits basically. So what we have here, again, there's our two little gaps or two little slits, and we're going to have some screen some distance away. And what's going to happen is when we have light, let's say we have a laser light. So if it's got a laser light and our laser, let's say it's going to emit red light. So the first thing you do, that red light obviously is just going to hit the middle there. So what I need to do is I have a single slit first, because that single slit is going to make that light diffract. So that light's going to diffract and spread out. And what's going to happen then, it's going to hit these two slits at the same time, exactly in phase, because they're the same distance away from that single slit. So now I'm going to have two waves that are leaving exactly in phase, and we can see that those waves are going to overlap. They're going to interfere with each other. They're going to superpose, and we're going to get a pattern formed on our screen. And the pattern formed on our screen is we're always going to get right in the middle. We'll call it the central maximum, because we're going to get a bright spot. And then we're also going to see bright spots on either side as well. So bright spots on either side. So we call these fringes. So fringes is where we see any of the bright spots. And the distance between the fringes, if you're doing AQA, we represent it with the letter W. If you're doing OCR, we represent it with the letter X. Okay. So we're doing AQA. The equation of this practical is W equals the wavelength times the distance between the slits in the screen divided by the slit separation. If we're doing OCR, what they're using this equation is that X equals the wavelength times the distance between the screen and the slits divided by the slit separation. So I'm going to focus on this equation, but you can see that W is the same thing as X and the S is the same thing as A. So if we look at the AQA one, what we're saying is all these fringe spacing is going to be the same. The fringe spacing, so W represents our fringe spacing. Our fringe spacing is equal to whatever wavelength of light we're using. We said we're using red light here from our laser. Our D is the distance between our double slits and our screen. So it's our capital D there, which you measure using a ruler. And S represents your slit separation. So the gap between those two slits there. So if I use my black pen now, again, it's the gap between those two slits. Or if I look at my slits on my film, it's the gap between those two slits. Okay, so again, what we said was the only way to see a pattern on the screen is that if the waves are coherent. It's really important you know what that word means. So you get asked to define it sometimes. So if asked to define what coherent is, you need to say that the waves need to either have the same frequency, or you can say they have to have the same wavelength, anyone you want, and you have to say a constant phase difference. You can't say same phase difference. If you say they have the same phase, you're not going to get the mark. You have to say it's a constant phase difference. So I'm telling you here, we said because we're using laser light, red light, that's our monochromatic light, light of a single color. So you take this one off, light of a single wavelength. What's happened is because I use my single slit to get the waves to diffract, and then because I've kept that constant between my single slit and my double slit, because they travel the same distance, these waves here are going to live exactly in phase. So we know exactly in phase from our earlier videos means that things arrive exactly in phase is 360 degrees or 2 pi. What that means is when a peak leaves one slit, a peak needs another slit. So we basically got our two peaks lined up and our two troughs lined up, which means when they interfere, when they superpose together, what we're going to get is we're going to get a wave that's got a much bigger amplitude. So that's going to form our bright fringe, which we call constructive interference. So that constructive interference is when our two peaks line exactly up because they're exactly in phase. However, what we could do instead is I could have one wave coming out exactly out of phase of the other. So let's say this one comes out at pi radons and this one comes out at 2 pi radons. So clearly the difference between them here, the phase difference is pi radons. They're exactly out of phase. So instead of me getting a central maximum that's bright, now I get a central maximum that is dark because the two waves, when they arrive at that central point, they're arriving exactly out of phase. And they arrive exactly out of phase, what that means is one of my peaks is lining up with one of my troughs, which means we can see that a peak and a trough would cancel each other. A trough and a peak would cancel each other, and we get a dark because we get destructive interference. We get nothing formed. Okay. So again, as long as there's a constant phase difference, we're always going to get coherent pattern. So what's that going to look like on the screen? So let's say, again, we're going back to our black example here. We're saying they leave exactly in phase. So they're leaving exactly in phase with a phase difference of 360 degrees or 2 pi. That means what we said here is going to be our central maximum, our bright spot. So what we see in a screen then is we look at our central maximum is we're going to see this peak of a central maximum, or we see our fringes, and then we're going to see our peaks on either side that all have the exact same width, that exact same W. So our central maximum with our peaks on either side. So again, we said all of them have the exact same width, or X if you're OCR A. Okay, so what we say is we call this one the n equals 0. The central maximum is n equals 0. The next ones we call n equals 1 on either side, and the next ones we call n equals 2 on either side. So this first bright, the second bright after the central maximum. And the pattern is, if the first one, the central one, is the central maximum of bright, what we say then is because n equals 0 times a wavelength. So 0 times the wavelength gives a bright fringe. So what we're saying is now anytime we see a bright fringe, we're going to be, the pattern is going to be, sorry, anytime we see a bright fringe, the pattern is going to be, it has to be a whole number of integers times the wavelength. So anytime we see a bright fringe, what we're saying is the path difference there is n times the wavelength. So if I just get rid of my blue lines now, so again, we're saying that they leave exactly in phase. What we're saying is that when I have a wave leaving slit 1 and hitting that central maximum, and a wave leaving slit 2 and hitting that central maximum, we can see their path difference there is 0, right? That's why it's called n equals 0. The path difference is 0, right? They travel the exact same distance because of those similar triangles there. So a bright fringe is n equals 0, so 0 times the wavelength. If I look at my next bright fringe, so if I look at the wave that's leaving slit 2, and it's traveling to the next bright fringe, and the wave that's leaving slit 1 to the bright fringe, you can see the wave that left slit 2 had to travel much further in distance than slit 1. And that further in distance, remember we just said here, is a whole number of integers times the wavelength. So we're saying that's going to be 1 times the wavelength. So the wave that left slit 2 had to travel 1 wavelength longer in path difference than the wave that left slit 1. So let's say the wavelength was 5 meters. So what that means is the wave from slit 2 traveled 1 times the wavelength, 5 meters longer than the wave that left slit 1. If we look at our next bright fringe, the wave that left slit 2 traveled 2 times the wavelength longer distance than the wave that left slit 1. So it traveled 10 meters longer than the wave that left slit 1. Okay, so that we're saying now any bright is going to be a whole number of integers times the wavelength. So all our brights, that's my 1 times my wavelength, that's my 2 times my wavelength. My next bright is 3 times the wavelength. My next bright is 3 times the wavelength. And anytime we see a dark fringe then, or a part that happened from our destructive interference. So again, remember, constructive interference was our peak and our peak. Destructive interference, we said earlier, was when we had our peak and our trough. It's going to be the integer plus a half times by the wavelength. So that's the path difference. So what we're saying here is when we see our first dark fringe, what that's telling us is the wave that left slit 2 that meet the wave from slit 1 traveled a half of a wavelength longer than slit 1. The next dark fringe is going to be 1.5 times the wavelength. The next dark fringe is 2.5 times the wavelength. So that's our pattern. So what we can say now is any bright fringes has a path difference of n times the wavelength, and any dark fringes have a path difference of n plus a half times by the wavelength. And we can then see what will happen when we change the wavelength. So you need to remember that we know that if visible light is the middle part of our spectrum, just change colors. So we can see that our visible light is the middle part of the spectrum. That's all our colors of rainbow. Richard of York gave battle in vain. Okay, the way I remember the electromagnetic spectrum is infrared is down here along with microwaves on our radio. There's really long waves. And then ultraviolet is up here the same way that X-rays are and gamma rays are. And there's really high energy short wavelength. Because violet is close to ultraviolet and red is close to infrared, red light always has long wavelengths, whereas violet light has short wavelengths. So let's say I want to change from my red laser light into my violet laser light. So if I just get my pen. So yeah, sorry. where is my pen? So let's say we change from our red laser light into our violet laser light. So again, instead of red coming out here, what I'm going to have is violet coming out here. And we're saying the wavelength is shorter. So what I've done is I've dropped the wavelength. What that means is my value of W decreases. So what that means is if W before was this separation, because it's decreasing, all of my brights are going to be much, much closer together now. So my fringe pattern gets much closer together. So again, W is going to decrease. So I'm going to have my central maximum, again, my peak of my violet light, and then the width stays the same. So you can see the pattern all gets squished into each other because what we did was we dropped the value of W because we use light of a shorter wavelength. So you see, we still have, remember, seeing bright fringes, but it's all been squished together.